Okay? And the father of dynamic is, as you know, it's Galileo. What he said is a dynamic a subject of never-ending interest, okay? So, what I'm saying is, there's no shortage of interesting problems in dynamics, okay? So first thing I do is, since this is first session, for those of you who are off campus, I will have the homework posted on the class website. So let me hand it out the homework first before I even start lecture, okay? So today what we're going to do is we're going to learn some things about dynamics. And let me see whether, is there someone in this class who never attended kindergarten? Did you go to kindergarten? No? Everybody went to kindergarten, right? Okay? So the guy who actually started kindergarten is a German guy named Froebel. Okay? There's a Friedrich Froebel. What he said is the following. Okay? So, in this class, if I paraphrase Froebel, this is a language of the things will be clear. So, this one is basically background. And the language of words in this context becomes equations of motion. So in other words, before we learn how to derive equations of motion, we have to know something about background, how to derive equations of motion. Okay? For example, language of things, for example, if you play in kindergarten, before you leave, you need to put all those toys and books back into the shelves, okay? Before you take a recess. So what we're gonna do today is we're gonna learn language of the things, means language of dynamics. Okay? A language of words means a language of equations of motion. So let's start. I think this is too hot. So what you probably have been learning so far is statics, okay? Statics, there are two things in statics. One is sum of forces equal to 0. The other one is the sum of a moment is 0. That's the statics. In dynamics, it's very simple. We carry over everything in statics, sum of forces, but this is by definition vector. That vector, which I will call F here, and there's a component, that's ith component, and then what I do here is the mass at the ith component, acceleration and ith component. This you can write in the following way. F, okay, applied plus F internal plus F inertia. And this F inertia is minus M if this is ith component I AI. Okay? The reason this is minus is the following. If you start the car, your body goes forward or backward? Huh? Backward? Huh? Or forward? Backward. Because it wants to be where it was. The car is moving where your body was over there. So it wants to go back. So acceleration is this way. Force is acting on your body the other way. When you want to stop the car, then your body goes forward, right? Because car is decelerating, the acceleration is backward. It's deceleration, okay? Acceleration is backward. Where your body, the force goes the other way. That's why inertial force is a negative mass times that acceleration. Okay? So that's why it becomes minus. All right? In the moment, it's a little bit different. Here, you can sum anywhere in each body system of free bodies. In the moment, you have to specify the point. Okay? You have to specify. Moving cannot be just arbitrary. You have to specify exactly the point. Then, if this is, say, at the position vector at P, has to be P from the P to whatever the point is, and then cross. So just like in translational force, you had MI minus AI. In the dynamics cases, the inertial moment is also same. It's actually the other way around. When your car is turning, okay? Car is going this way. Your body goes where? This way, right? When car turns this way, your body goes this way, right? So that's why same the meaning of negative, okay? So that's that. So it's very simple. Moving from statics and dynamics, all you have to do, put negative mass times acceleration. It's very simple, isn't it? In the moment, turn negative moment arm, cross inertial force. Okay? So you already learned this in your undergraduate, mostly second year. Okay? All right. So, but to get there, we have to know the language of things, language of dynamics. And there are several of those, and I'm going to introduce you. So now let's learn language of dynamics. Okay? So in doing so, I'm going to use a well-known problem. You already know how to write equations of motion. Okay? You already know how to write equations of motion without going through this. But since you don't have to pay attention to how to get the equations of motion, you pay more attention, I hope. Language of things. Okay? Language of things. So, example problem is this guy. Okay? So, that's easy enough, right? So some of you can even write the equation of motion without even knowing anything, okay? All right? So first of all we do in the language of dynamics, step 1. Choose or select your own inertial reference frame. Okay? If you write equations of motion without the notion of inertial reference frame, you're gonna flunk. So you have to know the notion of inertial reference frame. Inertial reference frame is the following. The origin can be anywhere. For this, I can put the origin over here, like that. Or I can put this origin somewhere there, even in Changwon. Doesn't matter, okay? You can put anywhere you want. As long as this guy moves either straight, constant, this guy can move with the constant velocity, okay? Constant translational velocity, okay? No rotation. And the constant include what? 0. 0 is a constant, okay? So including zero. And if you choose a coordinate system satisfying this, then this is an inertial reference frame. Okay? Now, if you write the equations of motion using inertial reference frame, then no matter where the origin is, 1, 2, 3, 4, we have 18 students, right? 18 of you will all come up with exactly same equations. I don't like your inertial reference frame. I'm going to choose it at, say, Daejeon, well, I don't know, one of the subway station. You could choose that. Or right here on the blackboard. Or some other room. It doesn't matter. No matter where you choose the origin of inertial reference frame, your equations will be exactly the same. Okay? It should not depend on where you put the origin of reference frame. Okay? But you have to make sure that your reference frame either translationally constant velocity, no rotation, including the velocity is 0. In that case, always a fixed point. Okay? So now I'm going to choose a reference point over here. Okay? So I'm going to choose over here. Now, when you choose an x, y, z, use a right-hand rule. Okay? X, y, z, x, y, z. Okay? X, y, z. This is right-hand rule. Okay? Don't use left-hand rule. Okay? All right? Now, in electrodynamics or quantum mechanics, there are cases you need this. But we're not talking about quantum mechanics in this class. So you use this right-hand rule. Okay? Okay. Because spin tensors tend to follow this guy. So that's a number one thing you have to note about the thing. Once you choose that, step 2. Now, for those of you who write the in the exam, don't choose step 1, step 2. In this course, you'll get 0. Make sure you put these things. Okay? There will be a problem in your exam doing this. So step 2 is obtain position vector. Okay? The reason is, if you follow this language of dynamics, when system becomes very complex, very difficult, you are not going to be able to derive equation motion correctly. That's why, even though I use a very simple problem, I'm going to lay out this language of things. Okay? Okay? All right. So I have that. Now, here's one thing you gotta do when you have this. By looking at this, this guy has no motion, right? So you pretend you create a motion for both M2 and M1, M1 and M2. So what you do there here is, this is a line, okay? And that is gravity-free state, okay? Now what we're gonna have here is gravity. In gravity field, this guy will come somewhere here, right? Right? Isn't that right? And this guy will say, let's just exaggerate. This guy will come here. Okay? Then I call this thing from here to there. I call that thing, say, y2. I call this one is y1. These are due to the gravity. Okay? But this is what the static solution is. In other words, y1, y2, when I apply, say, a load over here, this guy is not static case, this guy just is F. There's no T. Okay? And when you apply this F, if you have a y1 and y2, because of this spring will elongate, this is a static solution, right? Now let's now draw over here dynamic solution. So in dynamic solution, let's just exaggerate a little bit further. So this one I will call x2, and this one I will call x1. Okay? All right. So now I have a position, the position vector of this. Now, when you say position vector, it means mass point position vector. You got to remember, the only difference between the statics and dynamics is inertial force, which is signified by mass times acceleration. So position vector means where the mass is. Okay? So this is M1, M2, and this is M1. Okay? Now, this guy, I have to be careful. This guy is measured from here. In other words, I'm using two different inertial reference frame. This is O1, and this is O2. Okay? So this one is measured from here. Okay? This one is measured from there. Okay? Okay? So since it's a vector, I have to represent as a vector, okay? The underline in my lecture means vector, okay? Now, at this point, then it's very easy that acceleration is x1 double dot I, and acceleration over here is x2 double dot I. Okay? Now, you got to remember equation of motion, what we have here is x applied plus F internal plus F inertial, and we only know this guy. This guy is that one, okay? But we don't know this guy, and in this case this becomes due to the spring. So for this case, we write here for each of the spring, And convention is always use it as if it's extended. You can use a compression, but it's going to make your life miserable. So use it as if this is extended. In other words, here I use this one is extended, right? But equation of motion is independent whether you use this way, you squeeze it that way. Okay? And I'm going to have here, that's K2, like that. So for this case, the extended amount of, this is K2, K1. K2 is very easy, that's just X2. So the force, say F2, internal, is K2, X2. And let's take this guy as a positive quantity. Since I assume this guy is extended, so here, this one, I can have F2 as a vector, okay, K2, X2I. This one is F2 prime, which is equal and opposite, is a minus K2, X2I. Now this guy, to compute the spring force over here, we need to know how much this thing is really extended. And what happens here is, I could assume the original length over here is L1, here's L2. So this point here is, from here to there, it moves X1. But this point actually moved X2. So the difference here is, F1 here is, F1 here is K1, X1 minus X2. So again, this is a tension case, so that F1 as a vector is K1, X1 minus X2I. Here one is F1 prime is minus K1, X1 minus X2I. So we have a acceleration, we have a spring forces. Okay? So we are almost there, but we need one more language, which turns out to be the most difficult language in the language of things. Free body diagram. Statistically, when undergraduate engineering students pass through studying statics and dynamics, only about 1/3 are comfortable with the free body diagram. 2/3, they still struggle. Okay? Maybe not so in KAIST, but it's generally the worldwide. Only 1/3 of the students who took statics and dynamics are comfortable with the free body diagrams. 2/3, they still struggle. Okay? And this is where the rubber meets the road. So, please make sure you understand this. Okay? And I'm going to erase and just to make a mess over here. That is, free body diagram in dynamics means mass. Here's an M1, here's an M2. When we describe all the forces acting on the mass. Okay? So let's look at the M1. The M1, there's this guy, F. So we put the F here. Easy. Okay? How about the inertia force? Inertia force is this guy acceleration is this way. So inertia force is heading which way? Up. Up. So inertia force you can write here this way. But in vectorial there's no problem. It's minus m1 x1 double dot I. And this one is FTI. There is a force due to this spring. Okay? Which one, which force will act on the mass? Is this one or this one? Bottom one or top one? It's not that clear. I'll make it clear to help you. What happened is, when you say free body diagram, you break things apart. Okay? So for this free body diagram, it's like this. So when you break this thing apart, I'm sorry, Laoji, you cut here, right there. So now this guy was over here. That was F1. Okay? Therefore, when you cut this guy into two, there's Newton's third law. Action and reaction. Reaction is negative, opposite, right? So it's this guy. This guy turns out to be F1 prime. Okay? All right? So this guy also acts this way. Okay? That's a minus K1, X1 minus X2, I. Now, is there any other forces that we haven't considered? For those of you out there, is there any other force we haven't considered? There's one force we haven't considered here. What is it? Huh? Yeah, gravity. So this is a gravity field. Gravity acceleration is heading this way. So we have not considered gravity over here. And sum all this thing up. What do you get? You get equations of motion for mass 1. In other words, please remember, no mass, no equations of motion. In other words, we need to concentrate on the mass. This is what's different from statics. Okay? No mass, no equations of motion. Okay? So now let's look at the mass 2. Let's write down simple ones. Well, I noticed there is a gravity force, right? That's M2 G I. All right? I also know the inertia force. Inertia force is like that. Minus M2 X2 I. Okay? And on this mass, there are two springs. The K1 is acting at the top, bottom, and K2 is acting at the top. So we gotta put those two forces. So here it goes like this. This is K1. This is K2. So let me just exaggerate here. This is M2, M1 and M2, M2. So that is this guy, F2. This one is F2 prime. And bottom over here, there is this guy, F2 prime. So the one that acting on the mass is F2. Okay? F1, I'm sorry. This one is, F1 prime. And this one is F1. So here, since I'm running out of space, I'm just going to say here, we have here F1. All right? And there's this one is F2. F1, F2 prime. Sorry, the letter is small. So you sum all this thing up. And these are the two free body diagrams. And this is a body diagram for M2. Okay? Question? Everybody is with me? Everybody follows what's been discussed so far? Easy, right? When you practice it, that's when it's not so easy. Okay? Keep in mind the instructors normally use a simple example problems to explain the very basic ideas. When you saw my homework, right? When you are supposed to solve the problem, the homework problems is not as easy as this problem. Okay? That's why you are learning by solving homework problem. Okay? So now I can erase everything except leaving these two. Okay? So I'm going to erase. All right? So it's like the things that you have to do in your kindergarten. Play with all the Legos and put the Legos in the box, put it in a nice shelf before you leave. That's kind of a chore, but you're going to have to do these things. So the step 4 is very simple. Sum up the forces. Okay? It's very important. Acting on each mass. It's each mass, okay? You don't sum up this plus that. It's obvious, but I just want to emphasize that, okay? So let's do that. So for mass 2, which is this guy. So what we have here is minus M2, X2 double dot, right? plus M2G. So these two things are taken care of. Now F1 is plus K1 x1 minus x2. The other one is F2 prime. F2 prime is this guy. That's a minus K2 x2. I equal to 0. Since I can never be 0, this has to be 0. From that, by applying the minus 1, you have M2 x2 double dot plus, there's a x2 here, there's x2 here. So K1 plus K2 x2. And that becomes a minus because of minus multiplication. Then this guy was a minus, but putting in the right-hand side. So that is the equation's motion. Okay? Let's do the same thing for mass, which is this guy. So I have again M1 x1 double dot is this guy. Here plus Ft, apply the force. And this one is a plus M1G. And this one is minus K1 x1 minus x2. The reason why I carry I is, this case, one-dimensional, so it's kind of unnecessary, but you gotta do that, carry out all the vectorial components in three-dimensional cases, which is about your homework, okay? So by multiplying minus 1, and that's equation's motion. By combining this one, combining these two, we can write a real nice equation. So I can erase all this. Now let me emphasize it one more time. Okay? When you have this one, okay, it's not this one, it's not that one. It's when you cut. It's this guy. Cut and see the forces acting on the mass. Not this guy. Okay? It's very important. Everybody got that? Okay? So this is just to find out how the spring forces act on it. But in reality, it's this one. The force acting on the mass is the one you have to apply in the free body. Okay? This is the funny mistake that the students make. Okay? Never use this guy blindly. Use this one, compute this one, use this one acting on the, in other words, the action and reaction acting on the mass. Please think about one more time. when we say free body diagram, it's the force acting on the mass. It's not force acting on the spring, okay? Got that? Yeah. All right. So I'm going to erase this. So now you realize that the language of things are the ones that really makes us to learn dynamics, not the final dynamics equation, which we would use it, but the language of things are the ones important. Okay? Just like in kindergarten. All right? So today is the first lecture on dynamics. So you are learning language of dynamics. Okay? All right. Now, this x1 and x2 are the ones absolute displacement from the gravity-free positions. But if I sit down on this chair, okay? If I sit down on this chair like that, my body, so this guy already had a gravity. So this guy already has this y1 and y2 because it's got the weight. So when I sit down, add one more, okay? So I'm going to sit down abruptly so that it looks like a dynamics. Boom, okay? Then the sensor that I put it over here, the sensor that I will feel, it's not this guy, the sensor, okay? The sensor or sensors measure that one, this guy. It doesn't measure x1. And similarly, like that. So let me see how that really changed this equation. Okay? So that x1 is x1 prime plus y1, and x2 is x2 prime plus y2. So we just substitute these two, x1, x2. So first what we do is x2 double dot is x2 double dot prime plus y2 double dot. What's this guy? Do you know the value of this guy? Huh? Huh? G? What is this guy? Y double prime. Y differentiate twice. It's 0 because it's a static deflection. Once you made a static deflection, look at here. This is static deflection, okay? All right? This doesn't change with the time. When something doesn't change with the time, then when you differentiate with respect to time, what do you get? 0. Right? And all you see here is when I move this guy, all you see here is the difference between this 0 and that one. So the absolute acceleration is the same as x2 prime. Likewise, x1 double prime, x1 is x1 prime double prime. Okay? So we substitute this guy and that guy, number one, in this equation, so that m2 x2 prime double dot, okay, plus k1 plus k2 x2 prime plus y2 and minus k1 x1 prime plus y1 is m2g. Okay? Now I'm going to rewrite this guy. And then I'm going to put all this y2 and y1 on the left-hand side. And this one is minus k1 plus k2, y2. This one is plus k1, y1. And this is exactly static equilibrium. So this guy is a 0. This guy is a static equilibrium. Okay? In other words, let's do this guy. This guy is same way. M1 x1 prime double dot plus k1 x1 prime minus k1 x2 prime. Okay? And I have here is ft plus m1g and minus k1 y1 plus k2 y2, and this guy is a 0. So in terms of x prime, we have a nice equation. Like that. And this guy is M2. Like that. Let me say one thing, which is I really want you guys to understand the difference here. Okay? If I had a chalk, you'll get a chalk attack from me. Okay? Don't doze through in my class. Okay? If you want to doze through, go out. And then get the fresh air and come back. Okay? The difference between the total displacement, the x2 is total displacement. In other words, x2 is dynamic displacement plus a static displacement, okay? So this is dynamic. This is static. Okay? So if you write in terms of dynamic displacement, you won't see the gravity, right? If you have a total displacement, you will see the gravity forces. And don't get confused. Both of them are correct. Okay? And don't argue with your buddy next to your table, desk. No, this is correct. No, this is correct. No, I mean this is correct. Okay? The difference here is, that's why, you know, the step number 2 was what was step number 2? I'm going to make a random call. 김철우. 김철우 왔어요? 네. 김철우, 스텝 넘버 2가 뭐였죠? 네? 스텝 2가 뭐였죠? Position vector. That's why position vector is so important. Okay? I could have gotten position vector from here. Okay? Which is what x prime is. I could have gotten position vector from here. Okay? Alright? So depending upon how you chose a position vector, your resulting equation motion would be different. But the physical interpretation is different. This one is a truly dynamic displacement, okay, x1, x2 prime, whereas x1, x2 are the total displacement, including static displacement. Because I measured deliberately from gravity-free position. Okay? Yeah. Now, when the gravity goes away in space, for example, they become identical because when there is no gravity, y1, y2 are 0. So in space dynamics, it doesn't matter where you measure because there's only one measurement, which is, it doesn't matter whether you use this one or that one. Okay? But in ground, you will have this thing. And don't argue with your buddy next to your desk. No, it's correct to put the mg. No, don't put the mg. Okay? The confusion comes because you are not precise about what? The confusion comes, when does the confusion comes? Gravity term versus no gravity term. When does it come? When you did not put coordinate system. You haven't put the coordinate system. If you haven't this coordinate system put like this, you will have a confusion. So it's very important you have step number 2. Once you choose, so, hey, I'm a graduate student, I'm not going to follow you, you might say that, but since we are pretend that we are in kindergarten, okay? Step number 1, okay? Select an inertial reference frame. Let's say that, okay? Number 1, inertial reference frame. Number 2, position vector. Number 3, free body diagram. Number 4, sum up the forces acting on the mass. Yeah. See, when you hear, it's different. When you just look at it, sound, without sounds, you don't really register. And when you recite with the good voice, it makes a huge difference the way you understand. Okay? All right. So what time do I have now? We start, so we have 15 minutes, right? Right? Okay. Let me talk about a little different, again, very simple problem. So let me now erase all these and talk about already the equations of motion you already know. Yeah. You've seen this equation before in your physics or whatever, right? Somewhere, right? But I don't think you really went through what I consider the language of things. You gotta know this language of things to know to learn the words. Okay? So in the remaining 15 minutes, let's solve a very simple problem. And what I'm gonna do here is, I'm not going to just write it down, and I'm going to solicit your answers So I have a pendulum problem. This guy is a massless pop. Length is L. Okay? And I'm going to give a kick here. All right? So let's get, you already know the equations of motion, right? Let's practice the language of things. First of all, what do we have to do here? What? What is it? Inertial reference frame. So where would you want to have an inertial reference frame? And let me just imagine that this guy might have rotated this way. So what kind of inertial reference frame you want to put? Well, then we have a multiple choice. Do you want to have an inertial reference frame this way? Or do you want to have an inertial reference this way? If this is theta, I have theta here. Which one would you like to have? What? Yun Kyung-ho. Which one would you want to have? The left one or right one? Right? This one. Okay. All right. Why would you want to have this? Would you change this? Say, suppose theta is changed this way. So when you want to follow this xy like this, it's a very simple question. Say yes or no. Would you want to do that? Yes? No, time is running out. Would you want to do that or no? You will follow this pendulum? Is that it? Okay. Now, let's say whether this one satisfy the condition. What to be conditioned? The inertial reference frame. In order for a coordinate system to be inertial reference frame, number one, this is translational. Velocity is constant. Number two, Mr. Yun, do you satisfy this? Yes or no? The frame. This frame satisfies this guy, satisfies just translational motion, constant translation motion? Yes? How about the no rotational motion? Okay. You don't want to respond. So, 이감은, does this frame satisfy number one? Yes? How about the number two? Then, since this didn't satisfy, would this be an inertial reference frame or no? In fact, the V0 is not constant either, because it has to be constant everywhere. Here, 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 everywhere. The minute you rotate with this, unless this guy is constant, here is the velocity will be like that. It is velocity vector, right? Velocity is angular acceleration times arm, right? So at this point, this is velocity. So they are not constant. So neither one nor two are satisfied. So Mr. Yoon, you are out. That's why the concept of inertial reference frame is important. Very important. Now, let's say this guy, it doesn't move no matter what, no matter where the mass goes. Mr. Yoon, would this satisfy as an inertial reference frame or no? Why? What? What is it? Okay. So what he said was this guy satisfies, because in this case this V0 is a 0, right? Right? And then no rotation. So what I'm trying to say here is, you are in graduate school. Just because you can write down equations motion for pendulum for this simple case doesn't mean you understand dynamics. Okay? In other words, in graduate school, when you know certain things, you have to know for sure without shaking like that. From. And when somebody asks you, I know so because this satisfies such and such a criterion. Okay? All right? So, Mr. Yoon, if you are tutoring undergrad dynamics, you are not qualified today, at least for this problem. Okay? Now you understand? Okay. So let's use this guy. All right? And what we do here is, remember in spring case we used the notion of something stretched, right? Here we have to have a notion of something rotated. Okay? Like that. And for the sake of this problem, F is always heading this way. It doesn't follow, this guy doesn't follow like that. Okay? Okay? This is what we call conservative force. But we will worry about this force later. So, now we got this, and we know this guy length is L. We know the angle. Can we write the position vector R? What is the position vector? 이동석. Okay. You come out and write down position vector. This is one of the advantages when you have a white hair. I can ask students, young faculty will be a little bit cautious to ask students like that. At my young age, I can ask you guys to do this. Okay? All right. Thank you. So what you have done here is you have now specified unit vector along axis. Okay? All right. So all we have to do is just differentiate twice, right? And that's 8. And that is, turns out to be like that. Okay? All right. Now, question? What was it?
Our vector is L sine theta I plus L cosine theta.
Okay. Yeah. So when you differentiate this guy twice, it comes out to be.
Our vector is L sine theta, not cosine theta.
No, this guy is a sum of this one. All right, that's cosine theta. Okay, and this one is L cosine theta. This one is L sine theta. And this is an I, this is J. I hope I'm right. Am I right now? Okay. So now we have this. So this guy is massless, but there will be tension over here on this bar, right? So let me just say that as a tension as a lambda. I don't know what the tension is. And since I don't know the direction of this guy, I will just say the inertial force is minus ma over here. And then there will be a gravity, I. Okay? Now this problem, present a kind of somewhat problem. Because if I sum this guy in a translational motion, I'm left with the two unknowns and one equation. Because I don't know lambda, I don't know theta. Okay? So in this case, it's a pretty smart idea. Sum the moments at 0 over here. So if I make a sum of the moment, right? This reaction force doesn't contribute any moment, right? And all I have to do here is the distance from here to there is R, this guy R, okay? R cross MGI, all right? And this guy minus MA. And that has to be 0. Okay? So when you work that out, this comes out to be which you know, right? So here we do not use sorry. We don't use this equation. So now, this presents very interesting problem. If I use over here, say O prime, okay, if I use the position, the moment evaluation point over here, there will be lambda, right? Right? So that's one equation. Summing up this equation, I have one equation essentially. It's got two equations, but that really is the two equations. So summing up this one equations, okay? So in that case, I have one equation, we use it for computing lambda. The other equations, we use it for deriving equation of motion. You could do that, okay? So now the question is, let me just finish it. When you do that, we have three equations of two unknowns, okay? That's one equation more than what we need. And there's a hidden thing called a constraint. That is the length, okay? This one is, in other words, you take the adding both sides, you will have this guy. And you can express this guy A as x double dot I plus y double dot j. Then we have a two equation, okay, and one equation, and we can do this. But that's some other time. Today, what we need is we need a nice one moment equation to get the equation's motion, okay? And that wraps up today's class. And homework is due. Today is a Tuesday, right? There's only one problem. There will be one homework problem every lecture. So there will be, at the end of 2 weeks, we'll have a full homework solved, okay? Now, I expect you guys work 3 times the class attendance, which means the minimum that I expect you guys to work is 9 hours per week for this class, okay? That's what I expect. And so the homework, if you really know all this, the language of things, okay, you can do it in 4.5 hours, okay? Because I could do that in about 45 minutes, and for a very competent student, the factor of 3, average student factor of 6, compared with how fast I can solve. So factor of 6 is 4.5 hours. So have fun, and if you are really stuck, come and see me in my office. My office is W4111 and 5257 is my extension. Okay?